Let's talk about electric potential. Let's start with the definition. How much potential energy a charged particle would have at a given location. It is very similar to gravitational potential energy. So let's relate it. So say you have a mass at a given height from the ground. Potential energy is energy stored. In this situation, it'd be gravitational potential energy equals mass times gravity times height. And then you have a reference point. That's how you decide how much potential energy it has. At this situation, it's the ground. How does it get there? Work. Essentially, work causes a change in potential energy. Work equals force times distance. The force for electric potential is equal to Q times E, where Q is the charge and E is the electric field. So let's define the equation for electric potential, which is labeled as V, is equal to potential energy over Q, which is a charge. This is labeled in volts, and volts is equal to joules over coulomb. So let's write this in a more useful equation. Change in potential energy is equal to Q times change in electric potential. This is how you can use a battery of the same volt to power a scooter and a car. Obviously, the car is going to have way more potential energy, but let's use a scooter with a 10-volt battery with 500 coulombs of charge, and a car, the same 10-volt battery, but 50,000 coulombs of charge. So, change in potential energy is equal to 500 coulombs times 10. And you'd get 5,000 joules of energy. But change in potential for the car would be 10 times 50,000, which would get you 500,000 joules of energy, which is a lot higher of a potential energy. Let's talk about electric potential converted to kinetic energy. So let's use our example that we had earlier with gravitational potential energy. As the mass gets closer to the ground, velocity goes up, meaning potential energy goes down while kinetic energy goes up. This is how you get the equation change in potential energy equals negative change in kinetic energy. Let's do an example problem. So you have a 2 kilogram charge with 2 coulombs and moving at 5 meters per second. So we know that the change in kinetic energy is equal to 1/2 mv squared. So if we relate to the equation above, we do change in potential energy equals Q times change in electric potential energy to the negative 1/2 mv squared. So we are solving for the change in electric potential. So let's solve it for that. So it's negative 1/2 mv squared over Q. Let's rewrite this with our variables. Change in electric potential is equal to negative 1/2 2 kilograms times 5 meters squared over 2 coulombs. So we find our change in electric potential to equal negative 12.5 volts. So our potential energy is a decrease. Let's talk about electric potential in a uniform electric field. So let's draw this out. We would put the positive charge on one plate and the negative charge on the other. Let's draw our electric field moving from positive to negative, because this is the force that a positive test charge would feel if it were placed in the electric field. So the work done by the electric field is equal to work, force times distance times cosine theta. Theta in this situation is 0 because the test charge is parallel with the electric field, making cosine 1. So our force of a test charge would be Q times E. So work is equal to Q times E times D. So we know that work by the force Coulomb is also equal to work equals negative Q times change in electric potential. So let's set these two equal to each other. So when you set Q, E, D equal to negative Q times change in electric potential, you can cancel out the Q's on both sides. So then you have ED is equal to negative change in electric potential. So let's rewrite this as negative VB minus VA. Those are two separate points. If you redistribute the negative charge, it becomes VA minus VB. Let's do an example problem. So say you have a 500 volt over meter electric field. So what is the change in electric potential from 3 to 7 centimeters? So you would take the 500 volt over meter electric field times 0.04 meters, which is the difference between 3 and 7, and it gets you a change in 20 volts of electric potential. Now let's talk about electric potential created by a point charge. Let's define the equation to equal V K times Q over R. So you have a charge from a reference point, and the R is equal to the radius between the two. So K is a constant. It's 8.99 times 10 to the 9th Newton times meters squared over coulombs squared. So this is actually a scalar quantity, meaning it has magnitude but no direction. Let's do an example problem. So let's start with finding a reference point, which will be labeled by this dot that we've created, and 3 charges separate from this reference point. So we'll have 3 coulombs, negative 2 coulombs, 1 coulomb. 1 meter away from the reference point, 3 meters, and 4 meters. So with this, you just add the electric potentials of each charge. So K times 1 coulomb over 1 meter, K times negative 2 coulombs over 3 meters, then K times 3 coulombs over 4 meters. This will get you an electric potential value of 9.739 times 10 to the 9th volts. Now let's talk about equipotential lines that are created by a point charge. Equipotential lines are a change in electric potential equals 0, and this is because we have V equal to K times Q over R, where K is a constant and Q is the same because it's by the same point charge. R is going to remain the same because you're the same distance from the point charge, which makes V equal to the same value. Let's do an example problem and draw out these lines. So equipotential line 1, 2, and 3. Let's label them. The first one equals R, the second one equals 2R, and the third one equals 3R. Let's find the electric potential at 3R. So R equals 60. So we know K times Q is going to remain the same because we have the same point charge. So we know that's equal to 60V over 3R because it's 3 times R, and you get the electric potential to equal 20 volts at 3R. So along the same equipotential line, the change in V equals 0. So work is equal to negative Q times change in V, and when V is equal to 0, there's no work done along the same electric potential line. Let's do one last example problem dealing with electric potential. It is the conservation of energy and electric potential. So you have a 5 kilogram charge with 2 microcoulombs and moving 20 meters per second at A. What is it moving at B? So we have a point charge Q1 is equal to 2 coulombs. And then let's have a Q2 equal to 4 coulombs. And then we'll have point B here and point A here. So the distance between 2 coulombs and point A is equal to 8 meters, and the distance between Q1 and Q2 is 4 meters, and the distance between Q2 and B is 10 meters. And let's draw these dotted lines because we'll need them in a minute. Let's write out the equation of conservation of energy. KEA plus PEA equals KEB plus PEB. So let's find KEA. Half mass times 20 squared equals 1,000 joules. To find potential energy at A, we have to find the distance between Q2 and A. Let's change 4 meters to 6 meters. And this doesn't look like 90 degrees. Let's make it a 90-degree triangle. So we do 6 squared plus 8 squared, take the square root of that, and that gives us 10 meters from Q2 to A. Let's solve for potential energy A. To find this, we do Q times change in V. So we have Q equaling 2 microcoulombs times K times 4 over 10 plus K times 2 over 8, equaling 11,687. So now we have to find from Q1 to B. So we do 6 squared plus 10 squared, take the square root, and you get 11.66. So let's solve potential energy at B. 2 microcoulombs times K times 4 over 10 plus K times 2 over 11.66. And this will result in 10,275.54. Now let's rewrite the equation so that it's solved for KEB. So you have KEA plus PEA minus PEB equals KEB. So now let's solve it for velocity. KEA plus PEA minus PE divided by 1/2 times mass equals velocity, and you take the square root. So let's add our numbers. So we have 1,000 plus 11,687 minus 10,275.54 divided by 0.5 times 5. Kilograms equals the velocity. The velocity equals 31.05 meters per second at B. Thank you for studying electric potential with me. Here are my sources.